Bismillahirrahmanirrahim. Assalamu alaikum. Hello students, welcome to the Electrical Engineering channel. In this lecture, I am going to solve a couple of numerical problems to understand deeply the concept of electric flux density. So in the first problem, we are given a point charge of 0.25 microcoulomb located at origin, and we are given a surface charge density of 2 millicoulomb per meter square located at r is equal to 1 centimeter. This r is equal to 1 centimeter is a spherical surface whose radius is equal to 1 centimeter, and it is this surface, inner surface. And another surface charge density of minus 0.6 millicoulomb per meter square is located at a surface r is equal to 1.8 centimeter. So this is the second spherical surface, and the surface charge density is rho s2. Now we have to find out the electric flux density at r is equal to 0.5 centimeter. So for this surface r is equal to 0.5 centimeter, it will be lying somewhere over here. So this will also be a spherical surface, and within this spherical surface only this point charge is enclosed, and these two surface charge densities are actually lying outside this spherical surface 0.5 centimeters. So we can calculate electric flux density D very easily, and we just have to consider the point charge which is enclosed in this spherical surface. So D is equal to Q over 4 pi r square. We are given Q and R is equal to 0.5 centimeters. So D can be calculated as 795.7 AR microcoulomb per meter square. In the second part, the density has to be calculated at r is equal to 1.5 centimeters. So this surface will be lying somewhere over here because its radius is greater than 1 and smaller than 1.8. So it will be lying somewhere over here. Now this point charge and this surface charge is actually enclosed within this surface. So first we have to calculate the total charge within this spherical surface. So first charge is a point charge and second is actually the surface charge, and this surface charge density has to be converted to the total charge. Then we can calculate the density. So Q1 is equal to rho S1 into 4 pi r square, and r is equal to 1 centimeter, right? So Q1 will be equal to surface charge density multiplied by the surface area. So this is surface charge density. Area is 4 pi r square and r is equal to 1 centimeter. So this is total charge. Now this is the charge which is the surface charge for a spherical surface of r equal to 1 centimeter. Now the total charge will be the sum of point charge and this first surface charge, and it is equal to 2.76 microcoulomb. Now D is equal to Q over 4 pi r square. So this is QT divided by 4 pi r square AR. In the third part, same procedure will be applied. And in the third part, we have to calculate the electric flux density at R is equal to 2.5 centimeter. So this surface will be lying somewhere over here. And within this surface, all three charge distributions will be involved. This point charge, first surface charge, and the second surface charge. So let's convert the second surface charge to the total charge, right? So it is minus 2.44 microcoulomb. Add all three charges, and the net charge is 0.32 microcoulomb, and D will be equal to QT over 4 pi r square, and we have to calculate the density at 0.025 meter or 2.5 centimeter. So this is the density. And in the D part, we have to put another surface charge density at r equal to 3 centimeters to cause a zero electric flux density at r is equal to 3.5 centimeters. So from part C, we know that Qt is equal to 0.32 microcoulombs. So if we want a surface, if we want the electric flux density equal to zero, the electric flux must be equal to zero. And in order to get electric flux equal to zero, net charge must be equal to zero. So in order to make net charge equal to zero, we have to use Q3 equal to minus 0.32 microcoulomb so that it cancels out this total charge. So net charge is equal to zero, and at R equal to 3 centimeters, uh, This should be the total charge. So from this total charge, we can calculate the surface charge density, and that surface charge density is equal to Q3 over 4 pi r square. So this is Q3 and r is equal to 3 centimeters, right? So we should put a surface charge density at r equal to 3 centimeters. So the surface charge density is equal to minus 28.3 microcoulomb per meter square. That density must be available at r equal to 3 centimeters so that we get flux density equal to 0 at r equal to 3.5 centimeters. So that was very simple numerical problem, and I will also solve one more problem. And in this problem, we are given the electric flux density in Cartesian components in picocoulomb per meter square, and let's calculate the total flux passing through the surface z equal to 2 and x varying from 0 to 2 and y varying from 0 to 3, and here ds is equal to dx dy and az is the unit vector, right? So d dot ds can be evaluated easily, and ds has all three components but only z component will be considered because ay dot az will be equal to 0 and ax dot az will also be equal to 0. So we will just integrate this third component 16x square yz cube dot dx. So ds will be equal to dx dy, and let's integrate it. Limits of y, x and y are given over here, and z is also given as 2. So this final answer is equal to 1.365 nanocoulomb. So in the second part, we have to calculate electric field intensity at this point. So let's first calculate D at this point, and D field is given over here. Just put the coordinates of x, y, and z in this expression of this point. Then we will get D, and that D will be equal to this expression. So by mistake, I actually forgot to divide this expression by 3. So that's why I have written divided by 3 for these two components, and this is 1728 AZ. Now E can be calculated easily. So E is equal to D over epsilon. So this is D in picocoulomb per meter square, right? So this is a 1296. This is also 1296, and they are in picocoulomb per meter square. Pico means 10 raised to power minus 12, and epsilon is equal to 8.854 into 10 to minus 12. So those will be cancelled out, and we will just divide this 1296 by 8.854, here again 8.854, and here again. So it will be minus 146.4 AX plus this minus this volts per meter. So that part was also very simple. And in the final part, we have to calculate the total charge at this point if we are given an incremental volume of 10 raised to power minus 12 meter cube. So this total charge is equal to del dot D into dV, right? Del dot D is volume charge density, and if we multiply volume charge density with the total volume, we get the total charge. So let's first calculate del dot D. So del dot D is actually d partial dx over partial x. So the partial derivative of this expression with x, partial derivative of this expression with respect to y, and partial derivative of this expression with respect to z, and then add all of them and put the coordinates of x, y, and z, right? So partial derivative of this component with respect to y is equal to 0, and we get this expression. Now put the coordinates of this point 2 minus 1 3 over here, and at the end we get this expression for the divergence of d, which is equal to rho v. So multiply this rho v with the total volume, which is 10 raised to power minus 12. So finally we get this expression of minus 2.376 into 10 raised to power minus 21 coulomb, which is the total charge. So for a deeper understanding, I suggest all of you students to solve these problems. This is example 3.5, and this is the end problem 3.9, 3.13, and 3.21 of the textbook. And the textbook is Engineering Electromagnetics by William Haid, and it's sixth edition. So that is all about our third chapter of the textbook, and I hope you have enjoyed. and understood all the concepts which are discussed in this lecture series. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.